Okay, good afternoon. Let us start because it's 3 o'clock. So today we are sort of going to generalize a little bit what we have been doing till now. So there are two kinds of fields which we have considered till now. They are the fields QP, and there are these fields K bar series T, where K is a finite extension of FP. So these two kinds of fields have some common features, which I have tabulated here. First of all, they are actually fields of fractions of some rings, which are interesting. So in the case of QP, the ring is ZP, and the case of K bar series T, the ring is what we have been calling O, and it's K bar series T, but with only positive exponents. So integral power series, sometimes they're called. And both these rings are local in the sense that they have a unique maximal ideal, but they're not fields. Fields, of course, have a unique maximal ideal, but they are not very interesting from this point of view. So these rings are not fields, but they are local. And that maximal ideal is actually principal. So in the case of ZP, it's generated by the number P. And in the case of K bar series T, this maximal ideal is generated by the indeterminate T. Moreover, what we call the residue field, which is the ring modulo its maximal ideal, is finite in both cases. In the first case, it's just the finite field FP, and the second case, it's a finite extension of FP. That's what we had started with, a finite extension of FP, right? Finally, another property which these two rings share is that ZP is the completion of ZP ZP is complete, which means that the map from ZP to this inverse limit of over n of ZP modulo P to the n ZP, this map is an isomorphism. So that is expressed by saying that these rings are complete. Similarly, this ring O is, of course, the inverse limit of O modulo T to the n over n, right? I mean, it is just another way of saying that the power series, a power series like A naught plus A1t plus A2t squared and so on can be thought of as a limit of the following sequence, no? A naught plus A1t, A naught plus A1t plus A2t squared, and so on. You get this sort of a sequence, and the limit is, of course, this. So this is intuitively clear, but it is expressed precisely in this statement that O is the inverse limit over n of O modulo T to the n. Okay, so these are the features which these two kinds of situations which we have considered till now have in common. They have in common the fact that these fields are the fields of fractions of rings which are local, and the unique maximal ideal is principal, the residue field is finite, and the rings are complete for that with respect to that maximal ideal. So here is a definition which I have posed. I'm going to call a P field, P being a prime number, fix a prime number P, and a P field is going to be some field which is given as the field of fractions of a local ring, which is not a field. But the unique maximal ideal of that local ring is principal, and that ring should be complete for that maximal ideal. And moreover, the residue field should be finite of characteristic P. So that's what a P field is. This definition merely abstracts the properties which our two situations had in common. The common properties were that the fields QP as well as the field K par series T, they were the field of fractions of some ring, ZP in one case, K integral par series in the other case, which had a unique maximal ideal, and that maximal ideal was principal. The residue field was finite, and the ring was complete with respect to this maximal ideal. So whenever I speak of a K field, it comes with a ring which is sometimes denoted O sub K, and it's called the ring of integers of K. That ring has a unique maximal ideal, and the residue field is a finite extension of Fp. So it's sometimes denoted, K sub K, and it's a finite extension of Fp, if it's a P field, right? And here's the definition. A uniformizer of a P field K is just a generator of this ideal Pk. Of course, as an ideal generator, as what? As an ideal of the ring, as an OK module, so to speak, right? As an ideal of the ring OK, this Pk it can be generated by a single element, and any such element is going to be called a uniformizer of this P field K. Okay, so what is it that we are going to do today? We are going to show that if a P field has characteristic 0, then it is actually just a finite extension of QP. So the definition of a P field is a kind of abstract definition. It just says that, you have some ring O which has some ideal P, which has such that this O is the inverse limit of O modulo P to the N. And this as an ideal is principal. The ring is integral, of course. And O modulo P is finite. This is a field, right? Because this is a maximal ideal. That's all that was given to us. And of course, K is the field of fractions of O, sorry. So that's all that is given to us. And suddenly I'm saying that if K happens to have characteristic 0, then it's a finite extension of QP. This is what we are going to show today. Actually, we are going to show something more precise. But the other possibility is that the characteristic of K is not 0, but some prime number. If it has prime characteristic, then that prime number has to be equal to P, the same P as the characteristic of the residue field. This residue field O mod P was a finite extension of Fp. So it's a field of characteristic P. And I'm saying that this P field K, of course, this P is the residue field of K sub K, so to speak. I'm saying that if it does not have characteristic 0, then it has to have the same characteristic as its residue field. It cannot have some other prime number as its characteristic. And what we are going to prove today is that in this case, this K is isomorphic to the field K bar series T. So the two situations which we have been considering till now are the fields QP and the fields K bar series T. Now, by introducing this notion of a P field, we have enlarged slightly the fields that we are considering. In addition to this, and we are allowing finite extensions of QP as well. This is what we are going to prove today. So here is another name for this, the two situations which arise. So there is the field K, it has a characteristic, and then the residue field K sub K, which also has some characteristic. So the two possibilities are 0, P and P, P. So this is called the mixed characteristic case, 0 and P. Whereas here, this is called the equicharacteristic case. These are the only two cases. We are going to prove it today. And later, we are going to prove that conversely, if K is any finite extension of QP or of this, then K is actually a P field. So today we are going to show that a P field K is either a finite extension of QP or a field of this kind. Later, we are going to show that every field which is either a finite extension of QP or of K bar series T is actually a P field, etc. So let's start, let's get going. Now, so let's start with a P field K. And if you choose a uniformizer pi of K, then of course you get a subgroup generated by this pi in the multiplicative group K star, right? And in other words, what I want to say is that if I take a non-zero element in the ring O, then it can be uniquely written as pi to the power m times u for some m which is a natural number and some u which is a unit. Okay, so here is the proof. Now x, I'm taking a number which an element which is not zero in this inverse limit. So there has to be a largest index m such that x is congruent to 0 mod m and x is not congruent to 0 modulo m plus 1. Right? So which means that x is in p to the m, this power of the prime ideal p, and not in the next power. So if it's in this ideal, it means that x can be written as a multiple of p to the m because this prime ideal, the maximal ideal p is generated by my pi. Therefore, p to the n is going to be generated by pi to the n. So since p to the n is generated by pi to the n, my x can be written as a multiple of pi to the m, and this u is some element of the ring. But because x is not in the higher next power of p, this u has to be a unit. Okay, and this gives you immediately a corollary that the only ideals of this ring are the zero ideal and the ideals p to the n for every n. So this is exactly what was happening for ZP. The only ideals of ZP are 0, P ZP, P squared ZP, and so on. Maybe this 0 should be put here. Okay. So these were the only, because there are these inclusions like this. Right? P to the n ZP, basically these are the only ideals. And the other thing which follows from this is that the field K is just obtained from the ring O by inverting a uniformizer pi. Right? Because K is the field of fractions of O, and every element of O is just a power of this pi up to an invertible element of O. Therefore, if I invert pi, everything gets inverted. And the multiplicative group of K, the field K star, is just the direct product of the subgroup generated by pi and the subgroup of units, meaning the invertible elements of the ring O. Okay? And every element in the field can be uniquely written as a power of pi, but the power now is allowed to be an integer, arbitrary integer, not just a positive integer, times some unit, which is the same as an invertible element of the ring O. Okay, so we get, we can define this map Vk from K to Z union plus infinity. And Vk of x is going to be m if x is non-zero and m is the exponent of pi when I write x as a power of pi times a unit. And I define it to be plus infinity if x is equal to 0. So first, the first property that this has, this is similar to earlier we have come across Vp, which was a map from Qp to Z union plus infinity. And we had this Vt, which is a map from K power series T to Z union plus infinity. And this is the generalization to this abstract situation where this K is an arbitrary P field, and this Vk is also an evaluation in the sense that Vk of x times y is Vk of x plus Vk of y, and the Vk of a sum is always greater than the smaller of these two, of Vk of x and Vk of y. Okay, and so this ring O is just the inverse image of the positive integers, so to speak, including plus infinity, of course. And P is the inverse image of this thing here. So I think this is obvious, this is clear. And an element X in the field is in O star if and only if its valuation is 0. This Vk is called the valuation on the field corresponding, valuation on the P field. So this says that every P field comes with not only a ring of integers which has some properties, but it also comes with a valuation because of the properties of that ring of integers, right? And this valuation, some element of the field K is a uniformizer if and only if its valuation is equal to 1. Okay, so the next thing that we are going to do is to prove Hensel's lemma in this situation. So we have already proved it for K equal to QP, or in fact, I should say O equal to ZP. I mean, for this situation, we have done it. But now we are going to do it for an arbitrary P field K. So recall that P is a prime, K is a P field, and every P field comes with a ring of integers, and O is the ring of integers of this P field K. Okay, so what is the statement? The statement is that if I have a polynomial with coefficients in the ring O and an element of the ring O such that the derivative of this polynomial does not vanish at that element, f prime of x naught is not 0. Okay, so put delta equal to the valuation of f prime of x naught. So this is, of course, an integer which is positive, because f prime of x is f prime of x naught is an element of O, and every element of O has a positive valuation. That's in fact a characterization of elements of O, precisely the ones which are positive valuation. So here's the main hypothesis. Suppose that f of x naught is congruent to 0 modulo p to the m. Okay, where m is strictly greater than 2 delta. Delta has been defined here, and m is this exponent here. The important hypothesis is that m is strictly greater than 2 delta. If this happens, then the conclusion is that there exists a unique x, integer x, such that f of x is actually equal to 0 in the ring O itself, not modulo something, not modulo this power of the prime ideal, or no, exactly equal to 0 in the ring. And moreover, this x is close to x naught in the sense that the difference is congruent to 0 modulo p to the m minus delta. So m and delta were defined here, right? M and delta. And moreover, so it's uniquely characterized by these two properties, but it has this additional property, which is that the valuation Vk, it should be here, of f prime of x is equal to delta, which was, remember, it was the Vk of f prime of x naught. That was the definition of delta. Okay. Now, is there something in the here? No. Okay. So right. Now go away. Hello. Yeah, is there some question? Is there a question? No, fine. Okay. Now, you see, I'm going to prove this theorem, Hensel's lemma. In fact, most of you should be in a position to prove it for yourself. I'm not asking you to be very creative. I'm just asking you to be able to copy the proof which we have given in the case of ZP. In the case, as I said, in this case, we have already proved this, and I'm going to give you the same proof. So you might want to wink for a few minutes while I give it, because you want to try to give it for yourself, or this is going to be a kind of revision for you. So here is the proof. So let us first put x1 equal to x0, which is given to us, right? Minus f of x0 over f prime of x0. What is the valuation of this object, this whole thing? The valuation of this is the valuation of the numerator, or I should say it's greater than. The valuation of the numerator is greater than m, and the valuation of the denominator is exactly equal to delta. So, so the valuation of this thing here, f of x0 divided by f prime of x0, its valuation is greater than m minus delta, which is greater than delta because m is strictly greater than 2 delta, right? And which is greater than 0. Anyway, so the reason I want to say this is that this thing here is an integer, and x0 is of course an integer, so the difference is an integer, and moreover, x1 is going to be congruent to x0 modulo p to the m minus delta, this m minus delta here. Okay. So now I want to compute f of x1. x1 is by definition f is x0 plus something. So how do I compute a polynomial? How do I evaluate a polynomial at a sum? I use this identity, which we used even for ZP, which says that f of t plus s, here t and s are indeterminates, is equal to f of t plus f prime of t times s plus some polynomial gts. I don't care what that polynomial is. All I want is that, so that is some coefficient of s squared. In other words, I just collect together, I write f of t plus s, write it as a polynomial in s. Then there's going to be this constant term, so to speak. The important thing is that the coefficient of s itself is f prime of t. That's the only thing which is being said. And then there are terms in s squared, s cubed, etc. So I can take s squared common, and there's going to be some coefficient. I don't care what it is. So for some g in this OTS, I have this identity. Okay. So now I use this identity to plug in, instead of t plus s, I put this thing plus this thing. So I'll get f of x0 minus, this is the s here, right, with the minus sign, and this is the derivative, plus something times s squared. So now this whole thing here, things have been so designed that this whole thing is actually equal to 0. So what I'll get is the valuation of fx1 is here it is, is at least twice the valuation of this, which is valuation of x minus x0. I have computed it, it's m minus delta. So I can write it as m plus m minus 2 delta, and this is greater than 1, right? This here, m minus 2 delta, is at least 1. So in other words, f of x1 is congruent to 0 modulo p to the m plus 1. Whereas I had started with an x0, which was given to me to be congruent to 0 modulo p to the m. From x0, somehow I've contrived to get x1, which is just x0 minus f of x0 divided by f prime of x0. This simple sort of iteration has given me an x1 which is congruent to 0 modulo p to the m plus 1. So now I apply the same identity to f prime to compute f prime of x1. So I write x1 as x0 plus this difference. And so when I expand this, I'll get f prime of x0 plus this times sum s. And therefore, when I look at, now when I recall that the valuation of x1 minus x0 is m minus delta, which is strictly greater than delta. So the valuation of this thing is strictly greater than delta. So I'll get the valuation of this here is actually equal to the valuation of this, because the valuation of this was delta. And the valuation of this is strictly greater than delta. So here, this is something we have. Valuation of x plus y is valuation of x if the valuation of y is strictly greater than the valuation of x. Okay. So this is what I'm using here. Okay, so from x0, I've got an x1, which had the property that f of x1 is congruent to 0 modulo p to the m plus 1, and the valuation of f prime of x1, sorry, is still delta. Right? This is what we have. Now, if you iterate this process, if you iterate it, and of course, another property was that this x1 is congruent to x0 modulo p to the m minus delta. Was it m minus delta or m minus delta plus 1? Where is x? Yeah, here it is, m minus delta. Okay, so from x0, I've got an x1 like this. I can repeat this process. So I'll get a sequence xi, where f of xi is going to be congruent to 0 modulo p to the m plus I. In the case of I equal to 1, it was m plus 1. xi plus 1 is going to be congruent to xi modulo p to the m minus delta plus I. Again, yeah, this happens for I equal to 0, this is true. And v of f prime of xi is going to be the same as v of f prime of x0. So we get this sequence. This is a compatible sequence, and therefore it defines an element of O, because O is actually the limit, inverse limit of O modulo p to the n. Right? So I get this x is now an element of O. And it has the property that x is congruent to xi modulo this for every I. Now I have to show that f of x is equal to 0. This was to get hold of x. Now to show that it's a root, I just need to show that f of xi is equal to 0 modulo some power of the prime ideal, and which is what we have done. So we get an x which has these properties. It's congruent to x naught modulo p to the m minus delta. Its derivative, what is this? F prime of x naught is, yeah, okay. So these things I need in order to say that v of vk of f prime of x is equal to delta. In any case, so the summary. You have x naught is given to you. Then you define recursively xi plus 1 is xi minus f of xi upon f prime of xi. Well, xi, that's it. Then, in other words, you'll get a sequence. This has a limit x, and this is the one which is the one which we were seeking. It's a 0 of the polynomial f. Now we have to show that this x is unique. So we not only said there's a 0 x of the polynomial satisfying some condition, we also claim that there's a unique 0. So we will show something stronger, that if there is some y in the ring O, which is also a 0 of the polynomial f, and if just this y happens to be congruent to x naught modulo p to the delta plus 1, then this y has to be equal to x. In fact, x itself is congruent to x naught modulo p to the m minus delta, right? And this m minus delta is at least delta plus 1. So it could be greater. Now, in order to show this here, we use the same polynomial identity, f of t plus s, etc., and we'll compute f of y. By writing y, you write y as x plus y minus x. And then you compute f of y as f of x plus y minus x. So you'll get f of x times y minus x times f prime of x plus something else which I'm not really interested in, because there's this higher power of y minus x. So as x and y are roots of f, this f of y is equal to 0, f of x is equal to 0. So all I get is this whole thing is equal to 0. And I can take y minus x out from this. So I'll get y minus x times f prime of x plus y minus x times a equal to 0. What is the valuation of f prime of x? It's delta. That's what we have. That's the x we have constructed. The valuation vk of f prime of x is equal to delta, right? I mean, this is how x was constructed. What is the valuation of this thing here? The valuation of this thing is strictly greater than delta, because y, here it is, y and yeah, this should be an x here, right? Because y and the valuation of x minus y is at least delta plus 1. So it's strictly greater than delta. Here it's delta, here it's strictly greater than delta. And therefore the sum of these two things cannot be 0. Here, this is very easy to see, that if v of a is different from V of B, okay, let's call it Vk, then A plus B cannot be equal to 0, because here is a proof by contradiction. If A plus B is equal to 0, this implies that A is equal to minus B, which implies that the valuation of A is equal to the valuation of B. I mean minus B, but that's the same as the valuation of plus B. But I'm given that the valuations are different. So the sum cannot be 0. If the sum is 0, the valuations have to be the same. Okay, so that completes the proof of the uniqueness of X. Okay, I'm going a little slowly today, maybe. So here's an immediate corollary. If I have a polynomial with coefficients in the ring O, which has a simple root A in the residue field K. Of course, if I have a polynomial f in O with coefficients in O, then I get a polynomial which can be sometimes called f bar with coefficients in K, right? Because the polynomial f is f of t is a0 plus a1 t plus and so on, an t to the n, and this gives rise to a polynomial f bar of t is just a0 bar plus a1 bar t plus an bar tn, where these ai bars are in the field k, and it's a reduction of ai modulo the prime ideal or the maximal ideal p. Okay, so the corollary was that if I have a polynomial with coefficients in the ring O, and if it has a simple root in the residue field, then it has a unique root in the ring itself, which reduces to that root in the residue field. Moreover, this root in the ring itself is simple. Okay, so that's a corollary. We have proved that there's a unique root, but that it's simple follows from the fact that oh, wait a moment. Yeah. Oh, yeah, here it is. Yeah, so why is it simple, this root x that we had constructed in proving the theorem, in proving Hensel's lemma? It is simple because a multiple root is one in which is a root of x of f as well as of its derivative. But this x is not a root of the derivative because the valuation of f prime of x is equal to 0. If it's the valuation of 0 is plus infinity. If f prime of x had been equal to 0, then the valuation should have been plus infinity and not 0. But the valuation is given to us to be 0 because x is a simple root of f prime. So f prime of x is not congruent to 0 mod p. In other words, the delta is equal to 0 here, right? Delta was, yeah, that's right. Delta is 0. Anyway, so there you are. Now, I want to understand what are the coefficients. I mean, I have this ring O, which contains the ideal P, which contains P squared, and so on. And I want to understand what is P to the n modulo P to the n plus 1. What is that equal to? So, of course, all these ideals are principal, so I can they are all isomorphic to the ring O itself as O modules by just, you can choose a generator, P itself is generated by some uniformizer. So P to the N is going to be generated by the nth power of this uniformizer. So all these are isomorphic to as modules over the ring O, they are isomorphic to O itself. And when I choose an isomorphism like this, the ideal P gets taken to the ideal Pn plus 1. In other words, I have this map, O, when I choose an isomorphism with P to the N, it's N here, okay. And under this contains the ideal P, and that gets taken to P to the N plus 1. So when I take the quotient K here, the quotient P to the N, modulo P to the N plus 1 here, because these two are isomorphisms, I get this isomorphism. And that's what is being said here. So I've determined the quotients here, but then the multiplicative group, you have this filtration similar to what we had in the case of QP and little k power series T. So UN is defined as the kernel of this reduction map from O star to O modulo P to the N star, right? And you have this kind of filtration of K star. Here, we know that the quotient is actually Z. We know the quotient here, it's K star. What are the quotients here? In general, what is UN modulo UN plus 1? So it says that there's a unique isomorphism of groups from, this is what we wanted to compute. This is what we have already shown to be kind of isomorphic to K. So the assertion is that there's a unique isomorphism which takes X bar to 1 plus X bar for every X in P to the N. And this is, there's a unique morphism. Well, there's a unique map taking this to this, and it's an isomorphism of groups. That's what we want to prove. So first of all, we want to show that, X bar going to 1 plus X bar, it makes sense. In this, it doesn't depend upon any choices. So if X bar happens to be Y bar, then X minus Y is going to be in P to the N plus 1. And we have to prove that X plus Y bar, 1 plus X bar is the same as 1 plus Y bar, which is the same as showing that their quotient is in UN plus 1. So one way of seeing it is that if you look at 1 plus Y inverse, it's going to be equal to this. Now this makes sense. We haven't much discussed convergence, but it converges in the ring O. And you will see that, so 1 X minus Y is in P to the N plus 1. So this whole thing, 1 plus X divided by 1 plus Y is in U N plus 1. So it makes sense. And now we have to prove that it's a homomorphism. First of all, we have just defined a map, Pn modulo Pn plus 1 to Un modulo Un plus 1. We have just defined a map. Is it a homomorphism? It's going to be a homomorphism if, so the map was X bar going to 1 plus X bar. So what is X plus Y bar going to? By definition, it's going to 1 plus X plus Y bar. And the question is whether it's equal to the product of these two things. Because we want to show that it's a homomorphism from this additive group to this multiplicative group. So here is addition, here is multiplication. So you just check one for x and y in p to the n. What is the product? I mean, it's this. So you can check. So this shows that this thing is a homomorphism. I mean, this simple calculation that 1 plus x times 1 plus y is this thing, but this thing is in p to the 2n, and that is sort of sufficient to show that it's congruent to 1 plus x plus y modulo u to the un plus 1. So this map is actually a homomorphism. And why is it an isomorphism? Because I can give this reciprocal map, and this reciprocal is also, I mean, I don't even need to show that it's that it's a homomorphism of rings. It just needs to be a reciprocal in the sense of the reciprocal of a bijection. So if I have a homomorphism which has a reciprocal as a map of sets, then of course it has to be an isomorphism. A bijective homomorphism is an isomorphism in this kind of situations, right? Okay, so the next thing that I want to show is that for every r which is not a multiple of p, the map of raising to the power r from um to um, of course um is a group, right? It is um is the kernel, it's a subgroup of the group of units. U is the kernel of this map, this homomorphism of rings. So I mean, here it's at the level of units. So the raising to the power r map is actually an isomorphism if r is prime to p. It's not a multiple of p. So this is true for every integer r, but enough to prove it for positive integers, because for negative integers, I get it by composing it with the isomorphism x going to x inverse. That's an isomorphism because you have these commutative groups, right? Okay, so let's take an a which is in um and consider this polynomial t to the r minus a. Okay, and we will apply Hensel's lemma to this polynomial with the input x naught equal to 1. So for Hensel's lemma, you needed a polynomial, of course, but you needed an approximate root x naught as well. And so I'm going to take the approximate root x naught equal to 1. So what's the derivative of f at x naught? It's this is the derivative of f, and this is x naught. So, oh, where is, no, it's equal to 1, but its valuation is equal to 0. Valuation is equal to 0. When I put t equal to 1 in this, of course I get, or it's equal to r, in fact. It's equal to r, right? And the valuation of this r is equal to 0 because r is prime to p. So it's not congruent to 0 in O modulo p, which is of characteristic p. You see that this assumption is being used. Here. Assumption that r is not congruent to 0 mod p, or r does not belong to pz, or GCD of p r is 1. All these things are, of course, equivalent, and they are being used. And what is f of x naught? that was f prime. F of x naught is f is t to the r minus a, and wait a minute, what is happening here? So f of n x naught is equal to 1. So this is f of t. So f of x naught is 1 minus a. What is this? Yeah, that's correct. Okay. So we were forgetting, so it's 1 minus a. We were forgetting that this a isn't um. So a is of the type 1 plus b, where this b is in p to the m. So 1 minus a is of course going to be this f of x naught, which is 1 minus a, which is going to be 1 minus b. So it's going to be b, and which is congruent to 0 modulo p to the m. Okay, same m. Yeah, so that's what is written here. F of x naught is congruent to 0 modulo p to the m. But this m is strictly greater than 2 delta, because what is delta? Delta is 0. And m is at least 1, right? M is at least 1. That's what we are proving it for. There's no u0. M is at least 1, and delta is 0. So here m is 1 and delta is 0. That's what we are looking at. So m is certainly strictly greater than 2 delta. And therefore, by Hensel's lemma, we get a unique x in the ring O, such that x to the r is a, and x is congruent to 1, which was our x naught, modulo p to the m, which is m minus delta, because delta is 0. In other words, this x isn't um itself, because x is congruent to 1 modulo p to the m, right? So we have proved this, that raising to the power r is a bijection is an isomorphism from to of course, if r is prime to p. And m is greater than 1. Okay, now, just as in the case of ZP, we had constructed this subset R, which had the property that it was in bijection with FP, and it was a set of roots of t to the p minus t. That was the important thing. So now let us consider the subset R of O, defined as the set of roots of t to the q minus t, where q is what? Q is the number of elements in the residue field. So k is equal to O modulo p, and q is the number of elements. It's going to be some power of p. F is, it's some exponent. It's usual to write f in this context, but q is some power of p, and I look at this, the same power, which is the q is the cardinality of the residue field, and I look at the set of roots of this polynomial. Here it is. Okay. So the claim is that the reduction map from O to K gives a bijection between R and Q, R and K. It's a bijection. That's what I have to prove. So let F be this polynomial, and every A in the residue field is a simple root of F. Of course, that's because x to the Q is equal to Q, equal to x in k, right? Just as x to the power p is equal to x in fp, right? So why is, I mean, this shows that every x is a root, but why is it a simple root? Because there are exactly q roots, each of them has to be simple. If some of the roots had been multiple roots, you wouldn't have q roots in total, right? Of course, there'll be q roots with multiplicity, but some of the elements of k will be left out, which is not the case. Every element of k is a root of this polynomial t to the q minus t. So each one has to be a simple root. Now, by this corollary of Hensel's lemma, there's a unique simple root omega a in O such that, which is congruent to our given a. That's Hensel's lemma. Now, how many elements can R have? R is a set of roots of this polynomial. So the number of elements in R is less than the degree of this polynomial, which is Q. So R has at most Q elements. And omega is injective, right? Omega is a map from K to R, which is injective, because you can recover A from omega of A. So it's injective. Now, both of these, this has Q elements, this has less than Q elements. We proved it here, right? Because it's a set of roots of a polynomial of degree Q. And if you have an injective map from a set which has Q elements to a set which has less than Q elements, then of course this map has to be a bijection. You can't inject a set with Q elements into a set with strictly less than Q elements. So this map, omega is a bijection, and therefore this inverse, omega is the reciprocal map of this. It's also a bijection. Okay. So now I claim that if x and y are in R, then their product is also in R. So, a fancy way of saying it is that R is a submonoid of the multiplicative monoid O. O is a ring, so it has an additive, it's a group for addition, but it's a monoid for multiplication. So, and I'm claiming that this R is a submonoid for multiplication. And then I'm saying that the reciprocal bijection from K to R, omega, it's a morphism of multiplicative monoids, which is just a fancy way of saying that omega of A times B is omega of A times omega of B. So let's first prove that it's a submonoid. In other words, if x and y are in R, then their product is also in R. That's what we want to prove. So x is in R means that x to the power q is equal to x. Y is in R means that y to the power q is equal to y. Now I multiply these two equations, I get this. Now that's something which characterizes elements of R, that the qth power should be equal to the thing itself, which means that xy is in R. So if x and y are in R, then so is their product. Now I have to show that this omega is multiplicative, meaning omega of AB is omega of A times omega of B. Well, omega of A has this property. Omega of B has this property. So omega of A times omega of B is A times B modulo P, because this map is a homomorphism of ring. It takes products to products and sums to sums. So it takes this product to this product. But omega of AB, whatever it is, It's also congruent to AB modulo P by the definition of omega. Omega of anything is congruent to that thing modulo P. Now, by the injectivity of omega, you have to have omega of, no, not by the injectivity. Yeah, okay, injectivity. Because I've proved that this element here, the product is in R, because each of them is individually in R. That's what I've proved. If two elements are in R, then so is their product. Now look at this element and this element. They are in R by definition. So their product is in R. Now, this element of R, it's congruent to AB modulo P, but there's only one element of R which is congruent to AB modulo P, namely omega of AB. So omega of AB has to be equal to this element, omega of A times omega of B. So this omega of A is called the multiplicative representative of A, or the Teichmüller representative of A. Teichmüller was a German mathematician who did terrible things during the World War, but he was perhaps a decent mathematician. People do terrible things, and we are not going to go into it. We are going to pause for 2 minutes to see if anybody has any questions, and then we will continue. So you can unmute yourself and ask any questions. Okay, if there are no questions, let's continue. Now, as in the case of ZP, let's define R star to be this set of roots of t to the q minus 1 minus 1, right? So q, I recall, is the cardinality of little k, and q minus 1 is the cardinality of k star. So these are the q minus, the roots of this polynomial are going to be q minus 1th roots of unity, right? So these roots of unity, of course, form a subgroup of O star. And this R is just one element in addition to R star, namely 0. So omega takes K star into R star, and it's an isomorphism of groups. Another way of saying it is that, you know, I have this exact sequence here, short exact sequence here, O star to K star, that's the reduction map. This map is the reduction map. And U1 is by definition the kernel of this map. So till here it's exact. And of course this map is surjective. Yeah, so the exactness of the sequence is absolutely clear. And what is less clear is that this sequence has a section. In fact, we have already constructed it, and it's called omega, the Teichmüller section. And O star is the direct product of these two subgroups, K star times U1. So that's the general thing. I mean, if you have an exact sequence of commutative groups, A to B to C, and if you have this, if you have a section, a linear section, in the sense that not just a section as a, As sets, of course, there's a section always, because this map from B to C is surjective. But a section which is also a homomorphism of groups is what is required. And as soon as it has a section, okay, to simplify things, let's assume that we are in it's an exact sequence of commutative groups. So in this case, this B is going to be a direct product of A times, if the section is S, then S of C is going to be a subgroup, and B is going to be a direct product of A and S of C. So that is the situation here. This O star is of course commutative, and omega of K star is equal to R star. I mean, that's kind of the way things have been defined. This omega is in isomorphism. Yeah. So O star is K star times U1 as a group. Now I want to show that if the P field K has characteristic P, this P is the characteristic of the residue field little k. But if the big field K also has the same characteristic P, then this R is actually a subfield of K. No, not otherwise. Otherwise, it's not. Huh? So let's prove this. So we have already seen that it's a submonoid of the multiplicative monoid. In order to show that something is a subfield, you have to show that it's a subgroup of the additive group and a submonoid of the multiplicative monoid, right? I mean, maybe a fancy way of saying that if A and B belong to your subset, then their sum belongs to the subset and their product belongs to the subset, and maybe you want 0 and 1 to belong to the subset for it to be a subfield. Okay, so we already know that it's a multiplicative monoid, submonoid. So we have to show that it's an additive subgroup. So what do? We take two elements, X and Y in R. Because they are in R, they have this property. X to the power Q is equal to X. Y to the power Q is equal to Y. Now we are in a field of characteristic P. That's the hypothesis. And this Q is a power of P. So X plus Y to the power Q is X to the Q plus Y to the Q. But X to the Q is X and Y to the Q is Y. So X plus Y to the power Q is equal to X plus Y, and therefore X plus Y is in R. I mean, that shows that R is a subgroup of the additive group. And maybe that suffices to show that R is a subfield. And so I have this reduction map. It's a homomorphism of rings, of course, from O to K, because K is equal to O modulo P, right? And the claim is that this induces an isomorphism of fields. R is now a subfield, and the restriction of this reduction map to R is an isomorphism of R with the residue field K. I mean, this is clear because we know that it's because the reduction of X plus Y is X, the reduction of X plus the reduction of Y, the reduction of X times Y is the reduction of X plus the reduction of Y. Sorry, not plus, times, right? Times. And the reduction of 1 is 1. Okay, I mean, and what else? Nothing else is required. So that means that this, so it's a subfield of O, right? Of O, and this map is a bijection, and it's a homomorphism of rings. So it's a It's an isomorphism. Bijection plus homomorphism is an isomorphism. In this kind of situations, right? Because you should bijection plus continuous map is not a homeomorphism in general, right? But in this kind of situation, you are fine. Okay, so let us recall the notation. Our P is a prime number, K is a P field, and it has a ring of integers O, which has a unique maximal ideal P, and the residue field is little k, which has q elements, which is the power of P, and F is the degree, and R is the set of roots of this in O. Now, if I choose a uniformizer of K, which is the same as saying that pi is a generator of the O module P, of the ideal P of the ring O, then I can define a map sigma n from R to the n to the ring O. It takes the string A0, I prefer to think of R to the n as consisting of A0 up to an minus 1, where these AIs are in R. So it takes this kind of a family or sequence to this thing here, to the sum. So this is going to be taken to A0 plus A1 pi and so on up to an minus 1 pi to the n minus 1. So that's a map from R to the n to O. I'm calling it sigma n. Here's the definition again. And then, of course, I have sigma n here, and I can reduce it modulo p to the n, and I'll get sigma n bar. So I've defined these two maps from Rn to O and Rn to O modulo p to the n. So the first claim is that this sigma n is injective for every n, and sigma n bar is actually bijective. I'm not claiming that it's an isomorphism or anything. For I don't have any algebraic structure on R. Here it's a ring, and here it's also a ring, but R is not a ring. It's at most a multiplicative module, right? But it's certainly not a ring in general. We have seen that if the field K, the P field K, has characteristic P, then this R is actually a field. We'll come to it shortly. But right now, we are not assuming anything about the characteristic of our P field. K is any P field, and therefore R is not a ring or a field. It is just a multiplicative monoid, and I can only talk about bijections and so on. So the claim is that this sigma n is an injection and sigma n bar is a bijection. So here's the proof that sigma n is injective. So if I have two elements, A0, an minus 1, and B0, bn minus 1, which have the same image under sigma n. The image of the first one is this, and the image of second one is this. This is the image of the first one, the image of the second one. If these images are the same, if they are the same, then I can reduce them modulo p, or p or pi, and I'll get A0 bar equal to B naught, a B naught bar, because modulo pi or modulo P, all these things disappear, right? So if these two things are equal, then their omegas have to be equal. But omega of A naught bar is equal to A naught, and omega of B naught bar is equal to B naught, because A naught and B naught are in R. Huh? So if I have some element X in R, and I look at X bar in K, which is its reduction modulo P, and then I look at omega of X bar, which is again in R, then this has to be equal to X, right? That's how R works. That's how it has been defined. Okay, so I get A naught equal to B naught. That's so I can cancel it from both sides. There was an A naught here and a B naught here, but they were the same, so I've canceled them, and then I get this kind of an identity among the remaining things. But then I can take this P out and cancel it from the two sides, because I'm in an integral domain. No, I can cancel P out. So I get this sort of a thing. And now the same kind of argument will show that this A1 and B1, which are also in R, right? They are all these AIs and BJs, they are in R. So because A1 and B1 are in R and they're the same reduction modulo P, they have to be equal. And so on. I mean, I can continue this, right? So it doesn't stop here, and so on. You get AI equal to BI for all I in 0 to n minus 1. Okay, so why is sigma n bar injective? I have to show that it's bijective, but let's first show that it's injective. So we have already proved that sigma n is injective. And sigma n bar is obtained as a composition, right? You have, yeah. So sigma n went from R to the n to O, and then from O modulo P to the n. So I'll get a bijection of R to the n with its image, right? This is a bijection. And I want to show that this map here is injective, at least. I mean, if I show that this is injective, then this whole thing, which is sigma n bar, is going to be injective. So how do I show that this map from the image of Rn under sigma n to O n is injective? So the elements of sigma n p to the n, sigma n of Rn look like this. If I take some such elements, and if they have the same reduction, what does that mean? This is reduction modulo p to the n, right? It means that this element here, the difference of these two elements is divisible by p to the n. Yeah, that's right. Yeah, because if it vanishes modulo p to the n, it has to be divisible by this pi to the n, which is absurd. Unless a naught is equal to b naught, a1 is equal to b1, and so on. I mean, I have this element. How can an element like c naught plus c1 pi plus cn minus 1 pi to the n minus 1, when does pi n divide this? This can only happen if ci are 0 for all I. Okay, so finally, I have to show that this is bijective. I've shown that it's injective. This I've proved that this map is injective. And I know that the cardinality of R to the N is Q to the N, because the cardinality of R itself is Q, right? Which is the same as the cardinality of little k. And so in order to show that it's bijective, it's enough to show that the cardinality of this thing here is also Q to the N. So if I have two finite sets having the same cardinality and an injection of one into the other, then that injection has to be a bijection, right? That's how finite sets work. You can't inject a finite set strictly into some other finite set having the same cardinality. That's not possible. So I have to show that the cardinality of this is equal to Q to the N. That's by definition true for N equal to 1, right? For N equal to 1, O modulo P is actually equal to K, and this the cardinality of this is equal to Q to the power 1, right? So that's the N equal to 1 case. And then by induction, let's prove it for every N. So O modulo P to the N plus 1 will have this quotient O modulo P to the N, because P to the N plus 1 is contained in P to the N, which is contained in O, right? So when I take O modulo P to the N plus 1, this is going to in fact surject onto, surject O modulo P to the N. So here is a surjection. And the kernel is obviously P to the N modulo P to the N plus 1. So in fact, let's just take three commutative groups A, B, and C. And if I have inclusions like this, then I can take A modulo C that will surject onto A modulo B. And the kernel is, of course, going to be B modulo C, right? So that's what I've written here. This exact sequence is this and nothing else. And this kernel here is, I've shown that P to the N modulo P to the N plus 1 is isomorphic to K. So it has Q elements. And this has Q to the N elements by induction hypothesis. So this middle thing has Q to the N plus 1 elements. So now we have proved it by induction that O modulo P to the N has Q to the N elements for every N, and therefore this reduction, this map R to the N going to O modulo P to the N is bijective for every N, because it's injective and the two sets have the same number of elements. Okay, so let's look at this diagram. I mean, this is the map which I've been describing. This is for N, and the same map is there for N plus 1, of course. From the exponent N to exponent N, N plus 1 to N, I have this canonical map which takes x0 up to xn to x0 up to xn minus 1. So I drop the last term, okay? And here I have the projection that I've just discussed, right? Coming from the fact that P to the N plus 1 is contained in P to the N, which is contained in O. So that gives rise, to this, it's a surjection. Here also it's a surjection. And these maps have been defined in such, these bijections, the vertical bijections are such that they make this square commute. I mean, you go this way and then this way, it comes to the same as going this way and then this way in this square here. Maybe I don't know whether, anyway. And so what actually I get is an inverse system at the top, an inverse system at the bottom, and the inverse limit at the bottom is obviously this ring O. And the inverse limit at the top is this R to the N. R to the N consisting of all sequences x0, x1, infinite sequences of elements of R. So that's R to the N. So in the limit, I get a bijection sigma between Rn and O, which is the unique bijection making this sort of diagrams commute. I mean, that's how sigma has been defined, right? So you have these bijections sigma n bar for every n from Rn to O modulo P to the n. And in the limit, they give you a bijection sigma from R to O. So this is just another way of saying that every element of O can be uniquely written as as a sum. Every x in O can be uniquely written as A0 plus A1 times pi. So you choose a uniformizer pi, A1 pi, A2 pi squared, and so on. And this is the analog of what we did in ZP. Every element x in ZP was uniquely written as A0 plus A1p plus A2p squared. But the difference there, the difference between the case of ZP that we treated earlier and the case of that we are treating now is that there, these AIs were in the interval 0 to p to p minus 1. Whereas here, the AIs are in R. Then in the case of ZP also, we had a subset R. And so this result is new even for ZP. So elements of ZP can be written as this kind of sequences in two different ways. You can take the coefficients AIs to be the numbers between 0 and p minus 1, or you could take them to be p minus 1th roots of unity, which are, I mean, omega of fp star. That's what R is equal to in the case of ZP. No. Omega of fp, yeah, because 0 has to be included, not fp star. Yeah, that's what R was equal to. Okay, so I've exceeded 3 minutes of my time, of your time, and therefore I'm going to stop here today. And this is the time to ask any questions if you have any. I've been uploading the videos and the notes to that Google Drive link, which I've provided to you all. So you can look up there or send me an email if you have any questions. Okay, so I'll stop here.